Hello, everybody. My name is Anna Faust, and I'm a professor at the University of Bremen in Germany. It is my great pleasure today to deliver this keynote talk at the Global Humanitarian Technology Conference, and I hope you will enjoy a small insight into my work, which is mostly about underground sensor networks. So let's start. First of all, what I will be going to talk to you today. I would like to present to you the so-called MoleNet, which is a project which I'm running now for several years at the University of Bremen, which is about development of hardware and software for underground sensing. I will show you some sample applications which we have developed over the time. And mostly I would like to talk to you today, however, about how to make sense of all of these sensor data, how to make sense of the sensing itself. And some future directions, of course, should also be there. So first of all, what are actually underground sensor networks? In a typical agricultural setting, we will have some sort of an environment, some sort of an outdoor environment, outdoor field, which we would like, for example, to monitor over a prolonged time, let's say months or even years. And we will put some sensor nodes, which I will be talking to you a little bit later what they are, over this complete environment. So we're calling them simply nodes because they're really simple computers which you can put, in our case, you can put them underground. However, there are also many applications where you can put them over the ground. You can put them on a stick or some sort of a fence or another holder. In our case, we will be talking mostly about underground nodes. So you put some of those around the environment which you're interested in. Typically, the position itself of the node is dictated by the environment or by the sensing application. And what is important here is that these nodes are typically not connected directly to the internet. So it is a little bit different than the normal assumption of the Internet of Things, where each node can be addressed and can be accessed from the internet directly. Here, we would like to spare us this, let's say, overhead and these costs. And we simply say we're not interested in individual nodes, but we're interested in the data which is coming from the complete field. And that's why we're putting a base station, which is typically situated in the same environment as the nodes are, but it has internet connection and it has some more power supply so that it can serve the nodes well over the complete lifetime. And what happens next is that these nodes self-organize into a network, which, for example, this node here, which I just highlighted, is sending its data directly to the base station. This one also can do that directly, while these two here have to hop through another node in order to reach the base station itself. We call that a self-organized wireless network. Sometimes they are called also an ad hoc network. It really depends a little bit on the flavor of what networking technology you're using and which networking stacks and protocols you're using, which is not really part of this talk today. So this is the overall setting of what is a sensor network. And if you bury the nodes under, let's say underground, you get immediately an underground sensor network. In our case, we have been developing also the hardware for these nodes for many years now, well, many, approximately 6 years. And such one node looks in the environment a little bit like in this picture. So you have actually a relatively big box, which is big as this one maybe. And in order to put the sensor node inside, the sensors themselves are, of course, connected via cables outside of the box, which you cannot see here in this picture. And the idea is of having this box not only for waterproofing, but also in order to find it more easily later, because one of the problems which we faced in the very beginning was actually that we were burying our underground sensor nodes and we never got them back because they were so small and tiny that we couldn't simply find them in the ground anymore. So we started putting them in a little bit bigger boxes and well labeling them where we have put them, and still it's a big trouble to find them again later on, especially if a year passes or so. It becomes not trivial. So what is MoleNet? MoleNet is our underground soil monitoring project, which consists really of developing hardware, software, and applications for the underground environment. This is the picture which you already know, and this is how the box looks like. It is a self-developed sensor platform, which is Arduino-based. So we develop also the hardware itself, and we do order printing of the PCB boards. Then we connect different sensors and different modules to this platform in order to make it functional. We use a wireless communication over low frequencies, in this case 434 megahertz, which for the more experienced networking people here around, you will say immediately, oh, this is probably LoRa. This is actually not LoRa yet. It has been just a normal radio transceiver in this frequency, but now we're transferring slowly to LoRa directly, because it is simply easier to find the modules and to program at the end. This is how one of the first versions looked like. You will get into more details a little bit later. Here you see that the antenna is pretty much the biggest, which you can see the biggest component. And different sensors can be connected to this platform. The typical ones are the soil water content or temperature, humidity, pH value, dissolved oxygen, and so on and so forth. It depends simply on the application and on the purpose and the goal of your application which you're developing. And when we're doing experiments, you can see it also here a little bit in this picture. We're putting them in a depth of approximately 10 to 60 centimeters. This is where it works, where the wireless communication still works very well. And yeah, and you see here in this picture, you can also see not only the box, but also the sensor. This is the water content sensor, which is of course connected via cable and put directly into the ground. Here you have to be a little bit careful that you're not putting the sensor directly at the box, because then the measurements will be simply influenced by the box itself and the fact that it kind of catches the water around it. And of course, you have to be careful that once you install the box and especially the sensors, you put first of all a lot of water on the soil itself so that it nicely lays down. And only after a couple of hours, you can actually start getting the normal sensor data, which is the true sensor data. So it's not completely trivial also for installation and deployment when you're working in the underground environment. The MoleNet hardware, just to have a small idea about it, this is the so-called version 1. We're already working on another version, as I said, with a LoRa transceiver. Here in this case, we have just a normal radio transceiver working at 434 megahertz. We have, of course, a microcontroller. As I said, it is an Arduino-based system. What is important is the real-time clock, so that we always know exactly when the sensor readings were taken. Otherwise, in case of a restart or in case of a hardware failure or a small battery output and something like that, you will simply lose the date and time information on your system. Here on the right, you can also see the approximate cost of this platform. Without the sensors, however, like you see here that you don't have any connected sensors right now, the cost is not extremely high. It is the biggest, the largest, the most expensive parts are actually the real-time clock and the PCB printing itself. Especially for the PCB printing, that can be solved in a way that you simply order more of the PCBs. In our case, we always order 20 to 30, which is very, very expensive. And for all of the other components, it's of course, it matters how many you simply order so that you push the price also down. But this is the approximate price which we're paying currently. One of the first questions which always arise with the underground environment is whether we can actually get the data reliably out of the soil, out of the ground, even if we're going a little bit in deeper. So in order to understand that better, we did an experiment in one of our experimental fields in the University of Bremen directly, which is a specially prepared site where 2 meters of the normal soil has been removed and exchanged with pure sand. You can see that also very nicely here in the pictures. This is done for various reasons. First of all, it is a shared experimental field with sustainable environmental scientists who are testing different ways of reforestation for Saharan regions, especially in the south of Sahara. And for that, of course, they need a field which is resembling the Sahara sands. And for that, it has been actually developed. And I will tell you a little bit more about the reforestation in a few slides. So the first thing which we did here is to say, okay, should we go actually for 434 megahertz or 868 megahertz? Both of them have been used in the past in order to get the data out of the soil and to have a little bit more reliable and more reliable communication under the ground. And we have done several experiments here, which you can see the results here. In the middle of the slide, you see the packet losses at the two different frequencies. Above, you see it for 434 megahertz and below for 868 megahertz. And on the far right, you can see then the received signal strength. This is an indicator which is read the following way, that the lower it is, it's always in the negatives, but the lower it is, the harder it is actually to get the signal and to decode the signal which is coming. And you can imagine that approximately at minus 105, at minus 110, it actually stops working altogether. So let us look first a little bit into the packet losses here and understand what's happening. When we are looking at the graph at 434 megahertz and the one at 868 megahertz, we see very well that they have a similar behavior. So it works very well until some distance between the buried node and the base station, which is outside. You can see them here on the pictures on the left, like the base station is the laptop and the buried node is the one which you see in the hole, which has been buried for the experiment itself also completely. And you see, however, that the behavior might be exactly the same, but the number where it actually starts deteriorating, in other words, we start getting a lot of packet loss. It's completely different. For 434 megahertz, we got it up to almost 80 meters, 79, 80 meters. And for 868 megahertz, it was only 19 meters. For 20, it's already quite high, the packet loss with approximately 30%. So this is already a very clear sign for us that we have to use the 434 megahertz because it's much more long range. You know that also from LoRa. Than the 868 megahertz, which by the way is also frequency used by LoRa, especially in Europe. But still, you can see here the clear advantage of using lower frequencies. Unfortunately, we cannot go lower than that because they are not allowed to be used anymore for medical and research purposes. I already told you a little bit about the reforestation monitoring, which has been also part of the research, not necessarily of us, but of colleagues of us at the University of Bremen, especially of Professor Hartmut Köhler, who is also co-author of the paper which I have been citing here. And the idea here, you also see our experimental field, and the idea is actually relatively simple. The question is, or the research question is, how to push back the desert in the areas where it is exactly the border between agricultural fields and the desert itself. Of course, this border is not a line. It is some sort of an area of actually not that broad area, approximately 10 to maximum 100 meters, where you can actually drag or you can push back the desert in a way that you keep more moisture in the soil. And in this way, over the years, you can push really the desert back a little bit by 100, by 1,000 meters and so on. The question is how to do that. The problem is that once the rains are coming also in these areas. It's not the problem that there is no water at all, but once it comes, it floods everything and it puts away also all of the nutrients of the soil. It washes them simply away. In order to keep them on place and to keep also the moisture in place, the idea here was, and you can see it here very well, to put coffee bags, old coffee bags, which cannot be used anymore for transporting coffee for various reasons. You fill them with plant seeds and good soil, actually without fertilizers, just good soil and plant seeds. And you put them in various, you can see them here in various constructions around this area, around this field. And you see simply what happens. So once the rain is now coming, it soaks very nicely the coffee bags, but the moisture stays inside. They're also heavy enough and big enough to hold it there and not to be flooded away, not to be washed away. And we have put then our sensor nodes below these coffee bags in order to measure the humidity and to see how this develops over the months, over the years. This was actually our very first application, and this was the reason why we developed MoleNet in the first place. Then we discovered that this same hardware and the same approach is very, very valuable also for other applications. One of them is the so-called aquarium monitoring. This is also an application which jumped at us actually in one of my cooperation travels to Namibia, where I was talking to some colleagues in the campus of San Majoma, the University of Namibia. And they have been telling me about their problems with their fish ponds. Like here you can see such a big fish pond. The fish pond is a little bit bigger than what you would expect it from home. It is a pond like that, which is high approximately as my shoulders, like I'm not a very big person. It is approximately 1.5 to 2 meters in diameter. So it's a pretty big bath tube, pretty much, where different types of fish has been grown. And the idea, their research here is also highly interesting. They're trying to grow sweetwater fish or freshwater fish in salt water. The idea is that they have lots of salt water and very, very limited freshwater supplies. And on the other side, the people would like rather to eat the freshwater fish than the saltwater ones. They're doing that by putting the very tiny fish into these ponds and putting them first in fresh water and then very slowly increasing the salt level by very exactly also observing the dissolved oxygen levels and the temperature levels. The pH value is also very, very important. Once one of these parameters is, let's say, out of the limits and it's not okay anymore, the fish will simply die because it's not the optimal conditions. And this way you can very slowly increase the saltiness of the water, and then you can keep them growing in this salty water until they're grown up. So here you can see how we have used our underground sensor node in a new environment, which is of course obviously not an underground environment, but it's a very challenged environment. It is, first of all, it's a very humid environment because you can imagine that this complete hole is full of such fish tanks, and it's splashing water all over the place. In general, it is very, very humid as a whole, and it turned out to be Wi-Fi, for example, was not working at all there. And it turned out to be very, very good idea to use our underground sensor nodes with simply new sensors on board. So this time we're of course not connecting soil moisture sensor. That doesn't make a lot of sense, but we connected, as you can see it here on the picture on the right, we're connecting pH value sensors, dissolved oxygen, temperature, and so on. Salinity, we are not measuring directly because this is something which another system is doing anyhow. So we were monitoring simply, let's say, the vital parameters of the fish here. However, we wanted to talk today especially about making sense of sensing. Now you have seen a lot of applications. You see that underground sensing is actually not necessarily just a case of agricultural sensing in a field where you simply dig your sensors in order to get the water content out and to calculate how much you have to irrigate or how much pesticides you should be using. Instead of that, we would like to actually really make proper sense of the information which is coming out. So let's look into, first of all, some examples. So far, we have really seen how to sense, how we communicate this data to get it out of the soil, out of that challenged environment. We have seen many experiments. And I have not talked a lot about how to save resources, but this is also mostly part of our research, how to be very energy efficient, how to design the protocols and application in a way that they will survive together with the hardware, not only for several weeks or months, but even for years in the same environment. And the question is how to use this data and what to do now with this data directly. Of course, the raw data itself is very, very interesting to some experts, but typically people cannot understand very well what the data is and what to do with that. Let us see an example. That was one of the very first experiments which we did in Cameroon. And you remember the reforestation monitoring. And this is the data which came out where I said, well, I validated the system, right? The system seems to be working, seems to giving me values. Oh, I have no idea what they mean. I mean, is 14% volumetric water content, is it good or is it bad? What does it mean that it grows up to 16, almost 17? Does that matter? Is it important? Is it not? What is that peak at the very right? What does it mean and why does it fall down? I actually don't have any idea. However, when you talk to experts, they tell you immediately that, oh, this part, for example, of this graph is what tells the expert is that this is the so-called good rain event. They say this is exactly what we would like a rain to do. It comes, it puts some more water into the soil and the moisture stays there. It is not flushed away, it doesn't disappear, but it stays there in a very constant way. So such a step is something which is really good for an expert. On the other side, this event is what they call the bad rain event, or I'm probably oversimplifying here. They will probably not call it good rain or bad rain, but this is my interpretation. In this case here, in the bad rain event, of course, you immediately see, and after somebody explains it to you especially, that obviously a lot of rain came down, but the moisture disappears very quickly. And this disappearance of moisture just over the same day almost means that it flushes away, it washes out also all of the nutrients of this soil, which is of course something which you would not like to see. So you would like to do some engineering in order to prevent such a case. So with other words, there are some very important events in this data which are not obvious to non-experts. Even a farmer would not really know how to interpret this data. Also, the absolute numbers which I'm presenting here is something which I got used over the years, that these are normal numbers for soil moisture, like 14%, 24% is already actually very, very wet. And you have to get used to these numbers. What is normal? What is plausible? What is not plausible? 100% will not be plausible at all. This means typically that your sensor is simply broken. And 0% is almost not to be seen even in the middle of Sahara. So once you know such events, which is of course very important to me as a computer scientist and as somebody who delivers such services and develops such systems, once you know these events, you of course can use some machine learning in order to recognize them later. But it's a causal dependence, right? I need to know how such an event looks like. I need to have pretty much a database of such events already classified for me so that I can learn to recognize them later. And this is not trivial in interdisciplinary research, because people have only limited amount of time to explain to each other what they see and what to do. And they typically also lack understanding of what the other can do for them. So for example, in our case with the environmental scientists, we needed some years in order to get really in conversation with each other so that the environmentalist can ask me a simple question like, can you do that? And I can simply answer yes or no. And if it's a no, what else can I do instead? This is a very, very hard process, which is something which we as a community, especially in this conference, I think it's extremely important to push forward and to work for it, because interdisciplinary research for me is the only way to get out of almost all of our problems. Let us see what happens if some events are completely unpredictable. Here we have another graph, which is over time plotted different temperature readings from different sensors coming from the same fish pond. So again, a validation experiment pretty much, where the student who has been developing, you remember the Namibia fish ponds, wanted to simply see whether different temperature sensors work in a different way. So the first thing you can see here is that each color represents one different temperature sensor, and obviously they're different. The trend is almost the same if you exclude the blue sensor, but even with the blue sensor, you see that the trend of all of the temperature sensor is approximately the same. So if you're not interested in exact numbers, you can use any of those. Otherwise, you have to use one of the really well-calibrated one. The red one, by the way, is the real one. Okay, is the, let's say, the legacy one. What happens here? What is that? We don't know. Well, we don't know yet. It looks like a sudden drop in the temperature, which is kind of weird because Namibia doesn't suffer under winter of sudden winter breakages and things like that. So it looks weird in the first place. So that happened actually real time while my student was developing the system in Namibia. So she went simply over to the fish pond and looked what is happening. And this was happening. You see the fish pond? It is only just a little bit of water left in this pond, with all of the fish gathered at the very bottom of the fish pond and almost dead. What happened is that there was a leakage. It was a leakage in the fish pond, which just made the water disappear, leak out. So this is a perfect example of things which we don't predict. Even with what we have been discussing before with an expert and so on, the expert will probably also not know what is happening here. Maybe he or she will think about it, but this is not something obvious. This is not something which they immediately look at and say, oh, this is just an empty tank. Go fast because the fish will die. So such events, to gather such events is extremely difficult. And this is actually one of the challenges which we have, and which I will be also very happy to talk to some of you to see how we can solve these problems. So let us summarize. What are our challenges here? First of all, if we have known or expected events, if we have some sort of a database or discussions, interviews with experts, and we can identify important events, their recognition is, of course, not trivial, but it's absolutely manageable. We can use machine learning, neural networks, data science techniques, whatever else, in order to recognize those events also later. However, how to integrate such decisions into resource-restricted devices? So in our case, you have a very tiny platform which sometimes is connected via the base station or directly to the internet, as we have been discussing in the very beginning. But sometimes they're not. They take the decisions on their own. So for example, in the fish pond example, it will be nice if this sensor node simply immediately issues an alarm. Whether it's over the internet or it starts beeping and blinking, it actually doesn't really matter too much. But it's important that this sensor node knows what is happening and can issue an alarm or do something against it. Then the question is, of course, how to combine events from different technologies. In our case, we only had these sensor nodes put in various environments and not really cooperating with each other. But we would like to make a next step here and to say, can we combine information for underground sensing and, for example, remote imaging? Both technologies have their pros and cons. The underground sensing is pretty expensive, to be honest, and it's very it is very location based, right? Once you put the sensor node somewhere, let's say in imaginative scenario of where you would like to detect forest fires, you could use remote imaging and you can use underground sensing to put them all together. But the remote sensing will work only if the weather is good and you can actually see well. And the underground sensing is very expensive, and somebody has to go and to install these sensors over the complete forest. So both technologies need to be combined in a way and in a smart way in order to solve difficult problems like early fire detection. And of course, what we have seen in the slide before, how actually to recognize unknown events. What to do with events where you know that something weird is happening, you don't have an explanation of that, but you can nicely separate it from the normal events, from your known events, and you can say, this is something special, I need information from an expert, what is happening here? So with other words, to enable some sort of a proactive asking from the IoT system for more information from the expert, which is right now not there. And of course, coming back to the experts, it's very important how exactly to extract expert knowledge in a way that it's useful for the system. And you don't have to rely on, let's say, purely human-to-human communication to figure it out. What are the user expectations? This is also something which we have been bumping into over the years when we were presenting, for example, our MoleNet project at different fairs, at different exhibitions, where also end users were there. First of all, they would like, of course, to have a useful system with concrete action recommendations. With other words, if I give them the graph of the volumetric water content with my percentages, they will not know what to do with that. They cannot read it. They don't understand what it means. They don't know what to do, even if they understood what it means. So important questions which they would like to be asked are, which crop to select? Very important decision, not only for small farmers somewhere in Africa, but increasingly more important also for big companies and big farmers and agricultural industry as in general. When and how much to irrigate is a traditional question, but it's still very, very important. When and how much exactly, so to keep the system in some sort of optimal state. Of course, the same when and how to fertilize or to put pesticides, and which pest is it and what to do. So don't tell me it's a pest, but tell me what to do about it. What is also very important is to have some sort of a self-explainable user interface. This is, of course, a very, very active research area in the human-computer interaction. However, it still hasn't found the connection to the IoT sector, and especially not to the special IoT sector, which is serving humanitarian problems. We also would like to have an interface and in general a service which requires low to very low literacy. No literacy is probably not really realistic, but very, very low literacy will be already enough in order to understand our service and being able to use it. Low price is, of course, also very important, especially if we're talking about developing countries. And here we always have these two components. Of course, the low investment costs are important, but in fact, the investment costs are typically not the real problem. Because the investment costs, let's say, to buy a sensor node as we have it, or to buy even 10 of those, that can be supported by the government, that can be supported by NGOs, this can be somehow organized from microcredits and so on. This is something which people typically manage to organize. However, what is very, very important are actually the low maintenance costs, especially in terms of energy sources and connectivity. With other words, if I design my sensor node in a way that it requires a daily battery change or daily battery recharge, and it requires a full LTE connectivity, then it becomes simply not usable in many countries, and not only in developing countries, like also in Germany, we still have blind spots where LTE connectivity is simply not there. We know that from other projects which we have with German Shepherds, for example. And in order, like this is the real design challenge here. So this is also, of course, part of our research or of my group research, where we're putting most of our efforts is how to make it very long living and how to make the connectivity absolutely minimal and very low cost efficient. What is our ongoing work? We are currently working in integrating the so-called living labs in our design and development processes. What does that mean? It means that we're putting the humans in the loop of the development. So this is something which you probably have done in one way or another a little bit in various projects where you were simply talking to the users, getting some feedback from them, getting satisfaction surveys, and so on. However, a living lab is a little bit more than that. It means that the humans or the end users, and actually not only the end users, but all relevant stakeholders, are in the development process from the very, very beginning, and they work in different focus groups in order to identify for you different requirements, how the user interface should look like, what services are needed, how to present them, what kind of literacy is required, what is the good recharging process, and so on. So it is the same approach where you want feedback from your users, but instead of getting feedback about an existing product which you give them simply to test, you actually ask them to co-design the product with you. So other future directions which we're following right now is, first of all, how to use underground and weather data to make real recommendations on crops. One other idea is how to use sensing to identify different crop pests and minimize the usage of pesticides. This is something like both areas have been already explored, but I think not from the perspective also of having the underground sensing environment. And very importantly to me personally, in order to have more impact simply in this area, because I would like really our research to make a difference to somebody, to make a difference to a farmer somewhere in Cameroon or somewhere in Namibia, to make sensing actually self-explainable in order really to help these small farmers and the literate ones to get the most out of their farms, because otherwise they're more or less dependent on the big players and they will disappear with time if we continue in the way we're doing it right now. And I think the idea of integrating living labs into the whole IoT development process, now completely independent of the application, but simply into the IoT process, is something which definitely requires our attention. And this is something which we will be implementing in various projects also in the future. That's it from me for today. The questions and the discussions, I will take them obviously after the keynote. This is a recorded one. It's a little bit of a weird format, but I'm happy that we're still able to hold this conference. I'm very happy to take your questions later on. And if you would like, you can also contact me later also by email. Or by one of these other possibilities here, like the webpage or on Twitter. It will be nice to connect. I also have a blog where I'm writing sometimes, not very often. I'm not very disciplined in that, but sometimes I write also there. And one thing which might be interesting to the people who might be actually working in this area, I'm running a special issue on underground sensor networks with MDPI, which is still open until end of the year. Thank you very much and see you at the conference.